Alright, let's talk more about this rotational stuff, which is really cool stuff. Alright, let's solve this problem a couple of different ways. Give you some practice using these new concepts. So what we have here is we have a ball that is going to, you know what, now let's make that a cylinder. This is a cylinder that rolls down the incline. It has radius r and mass m. And it's released from height h equals 2 meters. So the center of mass of this ball right here is 2 meters above the ground at a 30-degree angle. All right, so first of all, let's use it. Let's solve this using acceleration. If we go ahead and take that object right there, and if we were to draw a force diagram for that object, we know that it has a normal force. It also has friction, which is perpendicular to that normal force. This is friction right here. And it also has a force of gravity, which is mg. If we take that mg and we go ahead and divide it up into its two components, we can say that mg is equal to, in this component right here, would be mg times the sine of 30 degrees. And we know this component right here is equal to mg cosine of 30 degrees. So we look at this force diagram, we can see that this force that is going down the incline right there is bigger than the force of friction. So we can say that the sum of the forces equals MA. And so mg sine of 30 minus that force of friction right there is equal to MA. Alright, so some basic Newton's second law stuff. We can also say that ball right there, that cylinder has a force of friction, which is going to, that's what slows it down right there. But it's also what makes it rotate. So that force of friction, which is applied at the outer edge, applies a torque. So we can say that the sum of the torques equals I alpha. So that force of friction times the radius is equal to 1/2 mr squared times alpha, which is going to be equal to A over R. And we get all kinds of cool stuff canceling out right there. This R cancels out with one of those R's, and that R cancels out with that R over there. So I'm left with the force of friction is equal to 1/2 MA. So using torque we get that. Using Newton's second law we get that. We can put the two together, and so we can say mg sine of 30 degrees minus, from over there, 1/2 MA, which equals MA like that. Alright, so we can now, then you can see masses cancel out. Masses are gone. We can go ahead and get this acceleration by basically solving the equation. So this is, we bring this over here, that's going to be 3/2 a. Left hand side over here, this is going to be g sine of 30. So basically g sine 30, this can be g times 1/2. Sine 30 is 1/2. And I get right there acceleration. Those cancel out right there. I get acceleration is going to equal g over 3. So it's about 3.3 meters per second squared. All right, so because of that rotational inertia, it doesn't quite accelerate as fast. If this object were just to slide down the incline right there, and we did the physics, we would find the acceleration to be 5 meters per second squared. But because it rotates right there, it has this rotational inertia. It's sluggish because of that mass it rotates. The acceleration is actually equal to 3.3. All right, the goal right here was to figure out the velocity at the very bottom. What is the velocity at the very bottom? So now that we know the acceleration, we can use kinematics. We can do this lots of different ways. Let's go ahead and use kinematics. So we know that this velocity at the very bottom, we can use a kinematic equation. How about we use this one right here? V squared equals V naught squared plus 2AX. And so if we go ahead and solve for that velocity, initial velocity is 0 plus 2. Acceleration we found was equal to g over 3. And the distance it travels down the plane, this is 30 degrees. The opposite side is 2. That means the hypotenuse is double that, which is going to be 4. So v squared is equal to, this is going to be 8/3. 8/3 times g. So we go ahead and solve that out right there. We get a velocity. Yeah, let's see, this is going to be 80/3. 80/3. So is that about 26 point something? Equals, let's see here. V squared equals 80/3. And then we go ahead and solve that right there. We get 80 divided by 3. And take the square root of that. We get about 5.2 meters per second. So about 5.2 meters per second. All right, so we're able to figure out the acceleration and use the acceleration and kinematics to figure out the velocity at the very bottom. Now, as you know, this is not the easiest way to do it. Let's go ahead and do the same exact problem and use easier methods. All right, so let's go ahead and take this thing right here. I love doing that part. And so energy is oftentimes a much easier method. So at the very top, we got potential. At the very bottom, we're going to have some translational kinetic, and we will also have some rotational stuff. So energy is conserved. Potential at the top turns into kinetic plus this rotational kinetic energy. So we got m gh equals 1/2 mv squared at the bottom plus 1/2 I omega squared. So we get m gh equals 1/2 mv squared plus 1/2. The I at the bottom is going to be 1/2. I'm not sure why it's at the bottom, but the I throughout is going to be 1/2 mr squared. Omega is going to be V over R, and we're going to square that right there. All right, we're going to solve for that velocity, and as you can see, this is a much easier method, and hopefully we get the same answer. We'll see if we get 5.2 or not. If we don't, then I will probably make this video over again. R will cancel out right there, and looks like nothing else cancels out. I don't think so. So we get G. We get G, and where'd my mouse go? Oh, there it is again. Boy. GH equals 1/2 V squared plus we get, is that 1/4? 1/4 V squared. And so we get GH is equal to 3/4 V squared. And so V squared is going to be 4/3 GH. And so V is going to equal to the square root of 4/3 GH. All right, so time of reckoning here. 4/3 times 10 times height of 2 meters. And do I get 5.2? Drum roll, please. So 20 times 4. Oh yeah, it's looking good. Square root of the answer. Yep, 5.2. Perfect. All right. All right, so 5.2 meters per second. So that's our answer right there for velocity. All right, so two different methods. Usually energy is the easier and better way to go. All right. I want to solve another problem and give you some more practice. So let's talk about these guys right here. We have a pulley attached to a ceiling right there, and we got a rope that pulls the pulley down, and there's a mass right there. I don't know, how about 2 kilograms? Sound good? Yep, sounds good to me too. 2 kilogram mass. As this mass falls, it pulls on the rope, which pulls the pulley. This thing is going to accelerate. It's going to come down here, hit the ground. Let's say it falls a distance right here of, what's a good number? How about we'll go crazy? 5 meters. Falls and hits the ground after traveling 5 meters. All right, let's go ahead and solve this problem 2 ways as well. Let's use both energy and we will use torque. So we'll start with torque first of all. So if you remember, if we want to figure out the acceleration of this falling mass, we can go ahead and we can evaluate it using torque. You remember the secret was to make sure and put a T right there and not 20, but put a T. And we can say that the sum of the torques equals I alpha. So we can say T times R is equal to, this is a cylinder. I didn't tell you that, but I am now. 1/2 mr squared times A over R. So cancel one of these, cancel over there, and the force of tension is equal to 1/2 ma. Just like that. All right, that's the torque equation right there. We can also look at this mass down here that's falling. And we know that mass is going to accelerate, right? Yeah, we do. All right, so what we can say is the force of gravity is 20 newtons. And the force of tension right there is T. So we use a little bit of Newton's second law of motion. We can say that F equals ma. Remember, we want to keep the acceleration consistent, so we're going to call this direction right here, we're going to call that positive. That was terrible. I cannot live with that arrow right there. Let's try it again. All right, so we'll make downward positive like that. So we can say that 20 newtons minus T is equal to mass 2 times A, like that. And so we've got two equations now, and you can see we got two equations, and we have two unknowns. So we put these two equations together. We got 20 newtons minus 1/2 ma. 1/2 ma. Let's see here. Just realize we got to be really careful right here because these two masses for these two equations are different. I did not give you the mass of this pulley, which it looks like we need. So we'll go ahead and say I originally gave you the mass of the pulley, which is 4 kilograms. All right. So let's continue here. 20 minus T, which is 1/2 that 4 kilograms I just gave you, times A is equal to 2A. So let's see, 20 minus that T, which is 1/2 ma, equals 2A. And we get 20 newtons minus 2A is equal to 2A. If we solve this right here, we get 4A is equal to 20. And acceleration will come out to be 5. So this thing is going to accelerate with the acceleration of 5. And the question is when this thing hits the ground, what is the velocity? How fast does it hit? So we can use kinematics now. Since we don't have time, let's go ahead, and this is usually equation works pretty well when you don't have time. Plus 2ax. So the initial velocity right here was 0. So v squared. So v squared is equal to 2 times a times the distance right there. The distance it falls was 5 meters. So we get v squared is equal to, what is that, 1050? So we solve that right there. We should get 7.1 meters per second. All right, that's the velocity of that thing when it hits the ground. How fast this thing is traveling. In fact, this whole string is traveling at 7.1 meters per second when it hits the ground. In fact, the edge of that pulley is also traveling at 7.1 meters per second when it hits the ground. All right, we want to do this using energy now and see if we can get 7.1. Hopefully it matches up. If it doesn't, I'm going to be sad. Okay, So let's go ahead and solve it using energy now and see what happens. In fact, it would be great if you would solve it using energy and press pause right now and then come back and compare it to what I got. That would be the most effective way to learn this right here. 2 kilograms, 4 kilograms, and it fell a certain distance. All right, so go ahead, press pause, and we'll come back and talk. All right, press pause. Hey, press pause. All right, so did you get a velocity of 7.1? If you did, then you're probably good. You probably don't need to watch the rest of this video. But if you just want to, I guess, verify or check to make sure I know what I'm doing, then please continue to watch. All right, so here's the idea. We're going to use energy. Using energy is a much easier method. To start off, we're going to say this mass right here that falls has a certain amount of potential energy. And when it hits the ground, it's going to have some kinetic energy. In addition, that pulley will be spinning, and that pulley will have some rotational energy. So we're going to assume this right here is a point mass, so that we don't have to worry about the height of this object right here. So this thing starts off having potential. When it hits the ground, it's going to have some kinetic. And then this pulley will also be spinning, which will be 1/2 I omega squared. All right, so let's go ahead and continue here. We have mgh equals 1/2 mv squared plus 1/2 I. This is a cylinder, 1/2 m r squared times omega is v over r squared. All right, I made sure and emphasize this mass is different than this mass over here. So we just can't cancel things out. So right here, r cancels out. Okay, my mouse is not working again. Has a little delay there. I'm not sure why. I'll keep on talking. I can't even press pause right now when this mouse doesn't work. Okay, come on now. What is going on? Are you going to freeze up on me? All right. Come on now, work. There we go. Boy, what is wrong with you? R squared cancels out r squared. And so once again, we're solving for that velocity. Boy, not a lot of things cancel out. That's not much fun, is it? So mgh equals 1/2 mv squared plus 1/4 mv squared. All right, I think I'm just going to plug things in. I know I tell you not to do that, but at this point, it's going to get pretty darn ugly. So I got a mass of, this mass is a mass, so you got to be careful with what we use for masses. 2 kilograms times 10 times height of 5 meters equals 1/2 the mass of the falling part, which is 2 kilograms times v squared plus 1/4. We're talking about the big mass now, which is 4 kilograms times v squared. All right, let's go to work. So this is going to be, what's that, 100? 20 times 5 is 100. 100 joules. This is going to be just v squared. This is going to be just v squared as well. So we get 2 v squared equals 100. And v squared is 50. Oh, I'm happy. It works out. So v comes out to be about 7.1 meters per second. So we were able to solve it using a different method, and we were able to get the same result, which is awesome. And I think you would agree this method is probably easier than what we did with acceleration. But you know what? If it's not, if you like the other method better, then go for it. Lots of different ways to skin the cat. All right, so once again, using basic models, we're able to solve some basic problems. So give these problems some try some more, have fun with it, and remember, physics!